All right, let's go ahead and get started. How is everybody today? Oh, hi everybody. How was Project 3? How many of y'all enjoyed Project 3? How many of y'all found it painful? It's probably the hardest project of the semester, okay? Project 3 is most likely the hardest project this semester. So let's talk about something. If I could have your attention, I can just turn up the volume if you need me to. Okay.
Let's just talk about something.
It's not working very well.
Let's just talk about.
That's much better. Okay, let's talk about pre-registration. Is pre-registration this week? That's what they sent me an email and said. So if, through some internal sense of masochism, you would like to take more computer science, then the courses that you would like to take next semester should be these two. Computer Science 052, which is Computer Science 2, and Computer Science 030, Math Methods. Now, the question you might be asking yourself is, why would I ever do this to myself, right? I mean, you just had a midterm. It was not easy. You just had a project. It was probably not easy and somewhat confusing. Why would you ever choose to do this to yourself? Well, let me try and answer that. First of all, parts of it are fun. How many of y'all have had fun programming? How many of y'all have had like this sensation that you actually accomplished something, that you solved a problem, and it was kind of a challenge and interesting and different, right? That part is good. If you enjoy that, then you get more of that. If you haven't enjoyed it, well then, you know, maybe this isn't for you. But parts of computer science are actually really fun, I think. And it even gets better than this, all right? This is, like I said in the beginning of the semester, a hard class. It's probably the most difficult class that there is in computer science. And the reason is because there is so much to learn up front, right? You have put in a lot of time, and now you understand about editors and compilers. You understand about running code. You understand about debugging. Think if we had to teach you, remember my crazy analogy in the beginning of the semester with like llama hair and knots on ropes and stuff like that, right? Try to teach you Incan. Like by now you've already figured out how to raise the llamas, how to turn the llama hair into ropes, how to tie knots and stuff like that. And you're getting to the point where you can really start to communicate and start to understand and do the cool stuff, all right? And as it goes on, I mean, this is like, you know, the very basic stuff. As it goes on, it gets even cooler and cooler. So let me give you a simple example of the kind of stuff that you'll be doing over the next couple of semesters, all right, if you stay in computer science. So we understand about vectors, right? Everybody heard of vectors? Let's say we had a vector, and in our vector was, I don't know, something big. How about information about every person by name that the NSA has ever wiretapped? How many people do you think the NSA has wiretapped? Millions? How many of y'all think billions? So here we have a vector, and this has billions of entries in it, okay? 1 or 2 billion. And let's say we want to find one person out of that vector. You just wrote a program that looks through a vector to find people. How do you do it? You use a for loop, okay? So we start here, and we start looking through. And there's billions of these. How long is it going to take to look up a person? It can take a long time. On average, if this is a billion, you're going to have to look through 500 million of these, on average, to find the one person. And the computer's fast, right? But still looking through 500 million things is kind of a pain. Yeah? Sure, you can start wherever you want. It depends on, okay, so this is what Math Methods is about, in part. In part. So if you assume that all of these things are just random names scattered throughout there, it doesn't matter where you start. Because on average, you're going to have to look through the halfway through before you find it. If it's sorted, then you can do more clever things, and we'll talk about that in a second. But I'm going to show you a really cool way to do this, okay? Now let's say we're looking for somebody's name. Whose name might we be looking for? Dave? All right, we're looking for Dave. Well, if we're looking through Dave and we're looking through this vector one thing at a time, it's going to take a long time to find Dave. So can we do better? And the answer is yes, we can. So instead of storing everything in single vector, like I'm not trying to be a politician, I know that was an echo of the last campaign, here's what we do. We store it in something called a tree. And a tree organizes data instead of in a big list So it splits out into pieces. And what we're going to do is our tree is going to have every single letter of the alphabet, A through Z. Okay. And each letter below this will have every letter of the alphabet, A through Z. And each letter below this will have every letter of the alphabet, A through Z, right? And we need a D-A. This one needs to have a bunch. And every letter of here will have every letter of the alphabet, A through Z. And one of these will be E. So now when we want to find Dave, instead of looking through this list of things one at a time, we just go, oh, Dave. We go D, A, V, E, and any records about Dave will be stored underneath there. So before, in order to find Dave, we had to look through 500,000 things. Now we have to look through 4. How many of y'all think that's pretty cool? That's pretty cool, okay? This is a data structure. It's called a trie. It's used for all sorts of things like that, where you want to look up stuff that has like a string ahead of it. All right. This is when you, so next semester, like math methods, will give you the tools on how to analyze how well these things work. Computer Science 2 will give you more language features so that you can do more with the language. And then you get, after that, next fall, if you continue going, you get to a class called Data Structures, and that is where things really start to rock. You learn all sorts of things like this about how to organize data in really efficient ways and how to build data structures that solve your problem that don't just have to look through a list of things millions of times. So it gets better. It gets pretty cool. Yes, sir? No, I don't. Sorry. I know it's available, but I don't know anything about it. But you know, all the math that you all have probably had has been like calc and algebra, and it's all very discrete curves and stuff like that. Well, we're dealing with computers. They have ones and zeros. Things are never like, you know, halfway in between. We have ones and zeros, and they're very discrete. So that's why it's often called discrete math elsewhere. All right, so computer science gets better. You keep having fun, but you get to even go to even cooler things, and you have all the basics sort of under your belt that you're starting now. Okay, so you get to do cooler stuff as you go along. Here's the other thing: it also gets worse. Now, here's why it gets worse for computer science students. How many of you all think this is harder than most of your other classes, like history and English and stuff like that, right? So here's what happens to computer science students. They go along, they're taking classes. It gets easier, but it's still challenging. And then you're hanging out with your friends, and who should I pick on, like art history, right? Or someone like that. And they're like, I have a paper due, and I have to write some stuff. And you're like, God, I have this huge program due, and I have to figure out data structures and math. You will end up working harder than your peers. And it is frustrating because your peers, and I've actually seen a document the university produced that shows the average GPA by major, so I know which major to go into if I want, on average, the highest GPA. And it is not computer science. We are not the worst, but we're down near the bottom, because things tend to be, it either worked or it didn't, you got it right or not. It's very discrete. There's not, you know, you managed to reflect a new novel way of interpreting this thing, and therefore you get a grade. You can't argue about it, right, as much. So it gets worse, and that's the hard part of computer science, is that compared to other students who aren't science students, you will be working harder and, you know, not always doing as well grade-wise. But then it gets better again. And when does it get better? You will have jobs, absolutely. At graduation time, our computer science students are like really highly sought after. And we have a special job fair. You can get internships your sophomore and junior years at places like Yahoo and Google and Amazon and the NSA, not to pick on them. But Georgetown, actually one of the units on campus, came out with a report recently about which graduates get the best paying jobs. And computer science students, number 2. Petroleum engineers were first, but you can't do that here. So in all the majors at Georgetown, you would probably be making the most money, if that is attractive to you. And you'd get a job quickly. And you can use it for anything. Okay, so there's my sales pitch. All right, so again, next semester, if you are interested in continuing, you really should take both. Let me say both of these are offered over the summer as well, so if you want to take one but not the other, you could, in theory, take it over the summer, or if you wanted to take this someplace else, you could. But This is the sad part about our major. This bothers me that you have to take 2 courses your second semester. And we had to get special permission from the university to allow our department to require that because it's kind of a pain, but it's necessary to get you into data structures. And once you're in data structures, that's like the, if you all play video games, like it's the one that unlocks all the other levels. So get to data structures. It's awesome. All right, questions? Sir? No? It's just that you need both of these to take data structures. Data structures is offered in the fall. And so if you don't take them now, you wait till fall of your 3rd year to take them. It's better to knock it out. Because once you get data structures, you can take all the different electives more easily. Because a lot of the electives require data structures. No, I think they don't. Less. I believe they are less. Seriously, this is the hardest course. This is the hardest course, and it's not by design. It's not like we're trying to crush your will to live and get you not to take computer science so that we don't ever have to teach and we can just sit around and drink daiquiris or something because there's no students, right? There's just so much to learn up front. Oh, the other good thing about computer science, I'll just jump on a conversation I heard before class. We don't have Friday classes. So, Tuesday, Monday, Wednesday, Tuesday, Thursday only. That's good, right? Are there other majors that have that? Yeah, they don't really teach you anything, though. It's all like how to dress nice and, networking and stuff like that. Okay. Early in the semester, we talked about doing flipped classroom stuff. We are starting that effective today. And so you all watched the videos, right, before you came? No, I'm kidding. We're starting effective next class. If you go on Blackboard and look under the Section 1 documents, there's something, a folder that says Flip Classroom, and underneath that, it says November 7th, and those are the videos to watch for next class. The videos were produced by Mark Malouf, who's a professor who also teaches this class sometime. He's from the South. You hear that in his voice when he speaks. Don't hold it against him. He's actually a very nice guy. Okay. And if you continue in computer science, you will eventually have him, and you can tell him I said that. So we go back a long way. So the videos are posted. Look at the next class. I am not requiring, I'm not going to have like a test or anything at the beginning of class to see that you've watched the videos, but 2 things will happen. If you have not, you will probably get, the videos are posted through Blackboard. If you haven't watched the videos, you'll probably get crushed because I'm going to assume that you know some of the stuff in there, and we'll work from there. I've turned on statistics tracking so I can actually see who in the class has watched what videos. And I'm very big brothery, and I can just take a look and see, who watches them and not. And what I'll do is either if not enough people are watching them, then I'll start having like a quiz at the beginning of class. But I don't want to do that, do you? No, nobody wants that. Or what I'll do is at the end of the semester, I'll draw a big correlation of who watched the videos and what grades they got, and see, how it correlates, and see if watching the videos is actually useful or not. All right. Everybody okay with this? It's about an hour's worth of videos, not much more. Questions about this? Okay, last time. All right, any final questions before we get down to work on stuff? Going once, going twice. Also, I am out of candy at the moment. I forgot to bring in the extra Halloween candy, so you will have to do without today. I apologize. Okay, so last time we were talking about scope. And we had written this program that showed us a lot of different features. When I say scope, what do I mean? What does scope mean? Yeah. Yes, scope means where a variable exists and is usable. Okay? And we have several different types of scope. We have global scope. Global scope means a variable can be used anywhere. And if we have a variable with name I, and then we declare another one down inside a particular block, which one is used? The block. Most local scope wins. Most local scope wins. So we had a global variable I, we had one inside a block, we had one inside another block. This was the more local block. We had an I that was a parameter, What do we know about global variables? They're a tool of the devil and cause people to die. All right. They're not bad from the point of view of the programs that we are writing right now, because you are the only one writing your program. They are bad from the aspect of like a large programming team. Like, say everybody in this classroom was working on the same program at the same time, which is how most software gets developed. The problem is that if you're working on your part of the program and somebody else is working on their part of the program, you can get strange interactions around global variables that are very hard to debug. They're incredibly hard to debug. Yes, which is what we do instead of global variables. All sorts of weird things will happen. So that's the problem, right? So if you have a global variable, you define a local variable with the same name, and then maybe you forget to define the local variable and you're working with the global variable and you're not even sure which one you're working with anymore. And then, our programs run in a nice linear fashion from top to bottom, but a lot of programs have multiple things running at the same time that are accessing things, and then that gets very complicated to debug. So, yes? Yeah, so the question was, can you in different functions have the same local variable or parameter name? You can, absolutely. Nope, they are unrelated to each other, as long as they are inside their own local block or function scope. All right, so then at the end of the class, I handed out a handout. How many of y'all have the handout? Anybody? So let's go ahead and take a look at this handout. I'm going to give you a couple minutes to work on it, and then we'll take a look and see what the answer is, and maybe I can dig out something. All right, let's go ahead and talk through this. I actually looked in my bag and I found one last special treat for the person who helps me, who wants a baby Ruth bar today. Yes, Kitty, go ahead. Let's talk through this. Where do we start? No. Don't jump ahead. Where do we start? Be methodical. Where do we start? We started int main. Is there anything before int main? What is that? So that is global. Is this a global variable? No, why not? So is it evil? Is it a tool of death and destruction? No, it's okay. All right, so we started int main. And we output. Great. And then? So the first time this gets called with? And it goes where? And this, what becomes 0? That I. So we had a block variable, and now we have a parameter named I. And we call, and what does k have? Yep, there's no parameter, there's no local variable, so this I is the global constant, which is, and it prints out 10. It goes back here, and then it prints out I, and the most local one is this parameter, which is, remember, was 0, prints out 0. And we return I. Does it get used for anything? Nope, there is no assignment operator, so it doesn't get used to anything. Okay, so that was 0. We do this again with 1. So 1 gets copied over here. We call k. K is going to be 10 every single time because there's no parameter or local variable. And then it prints out what was passed 1. It returns 1, which is, again, not used. We go through this loop again. We use 2. I is 2. 2 gets copied from the local variable I into the parameter I. We call k. Jump down here. Prints out 10. Jump back here. Prints out 2. Jump back here. Now the loop finishes. And now we call j of I again. Which I is this one? Why? Yep, we start looking back up. We say, oh, here was an I here, but it only is good inside those curly brackets. So we go back up and we find this I, which is 9. We call this with 9. It prints out, does this, prints out 10, prints out 9. So that should be what it prints out. No, global constants are fine. Global variables are a tool of the devil. Because global constants can never be changed because they're constant. Whereas global variables can be changed by other people. Yes, if they were trying to change a global constant, they would get a compiler error. If they were trying to change a variable, the variable would change. Yes.
So what's the point of declaring a global constant? Is it just basically to declare some sort of
Just like all the ways we used constants before, you can just make them global so that if you need to use them over again. So they're common. They're things like, you know, if you're doing mathematical calculations, pi or e or something like that. So, and depends on what problem you're working on, but they are pretty common. All right, other questions on scope? Scope of variables. I can pretty much, like with a very high probability, assure you there'll be a problem like this on the exam. Okay. Why are you smirking? Yeah, well, it'll probably be more complicated than this, though. So, okay. All right, last question on scope. All right, so let's do something a little bit new then. Whoops. All right, so here's our new program. Let's talk about functions and computing stuff. We all just used a bunch of functions. We all computed things. Did your functions have different names? The ones that you wrote for your program? Is it required for your functions to have different names? It is not. You don't have to have functions that have different names because the compiler can tell functions apart based on the parameters. And we end up using this. So, for example, let's say that we wanted to write a function that squares things. So here's our squared function. It's going to take an int, and it's going to return an int. And what is this function going to look like? How do we square a number? Do I have to send you all back to like high school math? Come on, fess up. Yes, sir. Multiply it by itself. Return x times x. So there we have written a function that squares an integer. Are we happy? Yes? How many are happy? How many are not happy? How many are in some sort of indeterminate state of being? All right. So this is very useful, but let's say we are writing the math library, and we want to have other functions as well. Say we wanted to have a float function. How does that look? How would we implement the squared function for a floating point number? Did somebody mutter the same thing? Who is muttering the same thing? Yes, sir, it's pretty much the same thing with one difference. What's the difference? With what? Oops. Yep. So, now we have a function. Before we could only handle ints, now we can handle floats as well. Is that good? All right. What else might we want to add to this? Are there other types that can be squared? Doubles? Great. How do we do doubles? The same way. So we write a function template. Double square double. Are we done? Have we covered every single type that can be squared? How many of y'all think we have? How many of y'all are pretty sure we have not? What else is there? How about short, unsigned short, long, unsigned int, double, long double? Do you want to go ahead and do all those? No, we don't. It's boring as hell. Okay? Nobody wants to do that. Nobody has time to do that. We're going to do something else instead. Okay? Here's what we're going to do. We're going to use something called a function template. And a function template is a very beautiful thing. It's a beautiful thing that allows you to write one function that will work with any type. Any type at all. So instead of having to sit here and go, oh, int, float, double, long int, unsigned int, short, character, stuff like that, all you have to do is create your function one time, and it will work with any type. How does that sound? Does that sound fun? All right, here's how we do this. So here's how we do that. First, I'm going to go back, and I'm going to get rid of all these functions because we're not going to need them. What we're going to do is we're going to declare one thing called a template. And here's what a template looks like. Sorry, parentheses. All right. The easiest way to think of this, is that the type itself is like a variable, right? You know that a variable can hold different values? Well, in here, what we're doing is we're saying we have a template that uses a class T. Now, class T is what's going to be replaced by int, float, double, long, whatever it is. Anytime the compiler sees something that's squared that has a type here and a type here that match, so as long as that's both things that are T are ints or floats or doubles, it will go ahead and create a function that uses that type. Does that make sense? I'm going to say it again because I don't think I explained it very well. But we're used to the idea that we can have variables that have values in them, right? How do you all remember variables? Everybody? Okay. Here, what we're adding is a variable that instead of holding a value, holds a type. And what we're doing is by this angle bracket class T, saying that this T can take on any value that is a type. Okay? So this T can be anything: int, float, double, long, character, unsigned short. Any one of those things we've learned about can be used to replace T. So this class T is essentially a variable that holds a type. Then when the compiler sees something squared, it will say, aha, it says int squared int. I will just replace this T with int, and I will have a function for ints. If I see something that has a double, I will have a function for doubles. Now let me just compile this really fast to make sure that I'm doing it right. Why isn't that working? And it compiles without error, so we are happy with that. All right, questions? Yes, so we're front to back. Yes, so every time we call this in main, if we say int x equals 2, and then down here we say int y equals squared of x, right? What the compiler will do is say, oh, I have this function squared that takes x. And it goes, well, I don't have a squared function that I know of, but I have this template. So it says x is an int, right? So okay, I'll replace t with int. This will be int squared int value, and now I know what to do. The same thing will happen should we use, double a equals, say, 2.3, and then we say double b equals squared of a, it will say, aha, it's function squared. A is of type double. I'll replace t with doubles, and now I have a function, double squared, double value. That matches that. I can do the computation. Yes? So I cheated. And here what I did is I put it above the main function. And so that's all you need to do. As long as it appears above the main function, it works. The reason we were doing... Anyway, does that answer your question? It's before, because the compiler works top-down. I'll get back to you all. Yes? Right. Yes, we're doing it all in one, and it appears before we end up using it anywhere, in essence, before main. Uh-huh. Yep. Okay, so what we're saying is we're going to have a template, which means we'll reuse it for many types. That the template is applicable to one particular class or type. Class in here sort of means types, and we'll talk more about classes today. And that what we're going to do is it's going to have one particular type t. And the compiler is going to say, okay, in this case it's an int. So the class t, any t that we see here will be replaced with int. So then it becomes int squared int. If we see it down here for a float, t becomes a float, and it becomes float squared float. So t is essentially a variable that holds a type in this case. And the class will change, right? You can put anything in here, any class in there, as long as you can multiply it, right? Because we're saying as long as this star thing works, you can put anything in there. You could put strings in there if string had a star operator. Anything. Yes, sir? The template is a reserved keyword in C++ to let the compiler know that what you're doing is a template that's going to be generic like that. Yes. Exactly. So if we wanted to write one for cubed, it would be something like template angle bracket class t angle bracket t cubed t value return value times value times value. Uh-huh. I don't know. I haven't actually tried it. You want to try it and see? I don't know. We should try it. Yeah. Yep, it'll work. This will work. Squared now, since we've used a template, will work for absolutely anything. Unsigned characters, anything like that. Nope, nope. So before, the example I showed you when I started was showing you that, look, and I dropped it someplace. What did I call that? So this is what we were doing before, right? Where for each single one, we had to declare the type over and over again. And we decided that sucked because there are just too many types. And the only thing that was changing between each of these functions was what? The type, right? So instead of doing it that way, we ended up doing it this way. And this is just a way of writing a single function that can work with any type. The type itself becomes a variable, as if it were, but the compiler does the substitution for you. All right? It's kind of weird because everything has been very strongly typed so far. Yeah? It will be, this will be a little bit confused because the way we defined it, we've said that it's returning the same type that it takes. There are ways that you can put multiple classes in here and have it return different classes. This is like the most basic template you will ever see in your entire life. They all get more complicated from here, but this is the only one we're doing in this class. Does that make sense? So you can do more complicated things. Yes, sir? We can put any letter here we wanted. This is just like a variable name. I just used T. Emily, you have a question? That was your same question? Okay. Yes, sir. Yep. Yep. so we did squared here. We could do a power that took two different types, and it would work the same way. You would essentially have, like, instead of t value, you'd have like t value comma t value, as long as it was the same type. Yes. As long as what you do in here works for that type, it's going to be cool with it. All right. Does this kind of make sense to everybody? Questions? Do you want to do one more? All right, let's just compile and see if this works first, because I've told you about it. So we should print out x and y, which should be 2 and 4, and then we should print out a and b, which would be 2.3 and 2.3 squared, which is what? I don't know either. We'll find out. Let's computer do it, okay? Computer's good at stuff like that. We suck at it. Okay. Whoops. I missed something somewhere. It would be helpful if I had semicolons at the end of the line. All right. So it printed out 2 and then 4, which is correct. Here, I'll clear the screen and run it again so it'll be at the top. So it printed out 2 and then 4. Is that integer 2 and 2 squared? It printed out 2.3 and 5.29. Is that correct? We're going to go with the fact that it is, right? It probably is. So let's just do one more of these really fast, just so we can try something else. Template, class. I don't know. Somebody wants something different than T there? Any good identifier should work. Z, you want capital or lowercase? Lowercase, okay. So we're going to do a power, z value, whoops, z base, comma, z exp. Yeah, this isn't going to work quite right, is it? Because we can't have a loop that does it anyway. So, but let's just see if this works. What can we do that has two things that takes a type? How about swap? You want swap? Swap is good, isn't it? Okay. Z temp equals base. Base equals exponent. This is my variable names are horrible now. X equals base, but we're just going to roll with it, right? And these things have to be reference parameters if we really want to switch them. Pardon? Oh yeah, thank you. This is what I get for thinking of new examples on the fly. All right. Okay, let me just see if this even compiles, and then I'll explain it. Please compile. All right. So here's what we're doing. We're coming up with a function that will swap two variables. And we want it to swap any type of variable that there is. So we're using a template. We're saying we're having a template, and the class is going to be named z. So z is going to replace whatever type it is. All right? So what we're saying is it's going to return. Actually, we don't even need a return. We can use void, can't we? So let's just clean that up a little bit. Oops. There, that's much better. Saying we're not returning anything, but we take one reference parameter of type z, which is going to be whatever, a second reference parameter of type z. Then inside this function, we need a temporary variable. And so we say, look, one more of these z things. So any place you see z in this method, in this function, is going to be replaced with the proper type. Z is now a variable that doesn't hold value, data like a value. Z is a variable that holds a type, which is weird from what we've seen. It'll be less weird as time goes on. All right. And so what we're saying is we set this temporary variable, swap them back, and when we're done, because they're reference parameters, they should be swapped. All right? Yes? No? No. Do you want it to be something else? This can be, I mean, I just ask people, this could be any identifier you want. You know? So I just changed that to doggy. You don't have to change it in your notes. I'm just trying to prove that it's just like a variable name. So it'll still work. So this is a variable. It holds the type, right? And so any place you see doggy, it's going to be replaced with whatever type is recognized in there. Now let's see if this works. All right, so if this works, we'll see it print 2.4 and then 4.2. It's ambiguous. What do you mean? Oh man, it was working so nicely too. That's what I get for trying to pull an example out of the air. All right, I don't know how to fix that right now, so we're just going to pretend that worked and moved on. Any questions? I should have stuck with a more simple example. I actually almost never use this. It's just something that I like to show you. I'm embarrassed. Please don't humiliate me any further. Yes? I swapped it because power wasn't going to work with every type. But I wanted something with 2 parameters. And I actually don't know why it worked. I'm going to have to go look and fix it for the next class. Yes? Yeah, you can do absolutely anything inside there. Yeah, and any place, it should be that any place you see this doggy or whatever, it will replace it with that type. So you'll get more of this next semester. This is like supposed to be the gentle introduction. Yes? No. So this whatever we're using here only has scope inside that template, and it just holds a type. Yes, sir? Okay, good. I'm glad. I want this to be over as soon as possible for me because it's not working and I hate it when that happens. Yes, sir? Oh, okay. I'm not sorry you're stretching. Okay, any last questions? No? So, templates, and we'll just pretend that one never happened. But this one works pretty well, and I'm not quite sure what the problem is with this one. And I don't want to have to spend time debugging it, so unless somebody already knows. No? I don't know either. All right. So let's take a second and stand up, stretch out, wiggle, do whatever you need to do. Not that many people dropped this class. There's a bunch of people who aren't here, I assume, because they stayed up all night doing their projects, and the second they turned it in, lapsed into a coma, and are probably now at the hospital or something like that. There are fewer people here today, but that tends to happen right after a project. So, yeah. So, yeah, people are sticking it out this year, which I think is great. So, okay, let's talk about something. Now for something completely different. Any Monty Python fans? All right, we're going to do something a little bit different now and for the rest of the semester. Here's what we're going to do. It's a little bit different, but it's incredibly awesome. Okay? Trust me on this. So, you all just worked on a project that involved people, right? Subjects. And each subject had certain characteristics about them. They had an ID, an age, a blood pressure, C-reactive protein, a couple of cholesterol measurements. I can't remember what else. Shoe size, was that in there? Something like that. There were a bunch of things in there. And it was really annoying to us, and particularly to Eamon, because instead of storing all the information about one person together, we stored each person's information someplace separately, right? And this was kind of sucky. We didn't necessarily like doing that. So let me give you a slight retrospective of where we've been, and then I will show you where we're going. So here is our timeline throughout the course of the semester. On the top, we had some data. On the bottom, we had some functions or instructions. You can call it whatever you want. And in the beginning, we had some individual instructions. And we could order those instructions together and they would do things, right? In the beginning, we had little pieces of data. And they all sat around and they did things. And as time went on, we moved from having separate pieces of instructions into real functions where we had a whole bunch of things that worked together, and we had these kind of little modules we could do things with. Right? Everybody with me on that? Does that make sense? And as time went on, we moved from having little individual pieces of data to a package or a container where we could put all sorts of pieces of data together. That was a vector. Everybody with me so far? And what we were working on is we were working with these functions that each took some of these data chunks to work on, right? You had your choice of how to write functions for the last project, which is actually what made the project hard. Sometimes when I adjust the difficulty of the projects, if I tell you what functions to write, it makes the project actually easier because you don't have to design your own functions. But you had functions, and how many of you wrote functions that used vectors as arguments, that took vector parameters, right? So you're passing these vectors around through functions. How specific were those vectors to your functions? Like when you had a function like compute Reynolds score, it had a bunch of parameters that were all vectors that were probably very specific and had to be in a specific order, right? And that was kind of annoying, wasn't it? So here's what we're going to do. We are going to remove this separation between data and functionality. And we are going to combine the two together. And we are going to have one thing that has in it some data, and that's going to have in it functions that operate specifically on that data. Everybody with me on that? Does this make conceptual sense to you? These things are going to be called classes. And what we're going to do now is instead of just having a bunch of data and functions, we're going to package them together in a way that makes sense. Yes, sir? Here's what we're going to do. Let me just finish describing. So, before, each person had essentially 7 chunks of data, and the data lived in 7 separate vectors. That was really annoying, wasn't it? Here's what we're going to have. So, for example, from the last project, we're going to have a class, and we might name the class a subject class. And the subject class will package together everything we need about one subject. What do we need to know about each subject? Yes, sir. Uh-huh. Some systolic. We need HDL, total, smoker, and history. And we can package all that data together into one package. Does that make sense? Yes, sir. Nope. It's a box, and it has all this stuff in it. It's not a row. It is not a column. It is a box it contains with it. And then we have, for each subject, we have functions that we want to call or provide as part of this. What functions might we have that work over all that stuff? Yeah. The Reynolds score, right? So for a particular subject, we might say, hey, tell me your Reynolds score. And that subject would say, oh, I have a method, a function that's going to turn out to be called a method that says, oh, Reynolds score, and I already have all the data inside me that I need to calculate that. Does that kind of make sense conceptually? So, C, back in the early days, C++ was based on another language called, and what is the difference between C and C++? Yes, C++, and we all know it's like the increment, is an object-oriented version of C. These things, these classes, are used to create object. So, a class is like a blueprint. And an object is the building that is built using that blueprint. Are you happier now that we're here? All right. So a class is like a blueprint, and an object is like the building built using a blueprint. If I give you one blueprint, how many buildings can you build using that blueprint? As many as you want. Okay? As many as you want. So a class is like the design or blueprint, and an object is the instantiation or creation of that object based on the blueprint. Yes? This is just one person. If you have 1,000 people, you have 1,000 of them. What can you put those 1,000 people in? A vector. Because what's going to happen is because a vector can handle things that are all the same, right? If you have a subject class, you can say vector angle bracket subject and stick 1,000 people in the vector. Does that sort of conceptually make sense? All right, does everybody kind of understand this concept? Just conceptually, does it make sense? Without going into the mechanics of how we do it, which is what we're going to spend some time on. And in fact, Project 4, which will be posted when I get around to it later today or tonight, is a version of Project 3 over again, except doing it this way, which is going to be a lot neater. You'll see. The code is much neater this way. All right, how y'all doing? All right. So the rest of the semester, we're going to be working with classes, and we're going to be working with objects. Let me tell you a little bit about why we do things in object-oriented style. The reason we do it is because once we have created an object, in theory and in practice, we can reuse that particular object over and over and over again for different things. And the idea of object-oriented software arose because people were writing all this stuff with like functions and little bits of data, and it was really hard later when you wanted to write another program to kind of adopt and reuse the stuff that had been done earlier. And the idea is that if we can design our classes and we can design things that support classes well, we can reuse them over and over and over again, and we don't have to write extra code to do so. Now, there is a trade-off. How many times have I told you in this class to be lazy? Right? Lazy is good. Lazy is good. Minimal effort for maximum achievement. Classes tend to be a little bit more work up front. That is, it takes you more effort to design a class and to get it working. Well, I take that back. It takes a little more effort to design and actually code the class. But it's easier to test and verify that it's working, and it's easier to reuse. So it's one of those situations where you put in a little bit of extra effort up front, and it pays off later. You all familiar with that concept? Right? So it's a little bit annoying because some of the overhead in writing classes gets a little bit awkward, but then it pays off when we can reuse it. And it really pays off because it's easier to test and make sure your code is working. So let me just tell you something that we don't do in this class that we might someday in the future is when people are writing like software in a big company, they will sit down and instead of like writing code, they will design how all the objects exist and how they are supposed to hook together. And there's special diagrams you can do this. And they will design this big diagram of all the pieces that are supposed to be there and how they interact. And then what they do before they code anything is they sit down and they write all of the test cases to prove that each one of those things works correctly. So before they write any code, they write the testing component or the test framework to make sure that when they write their code, they know whether it works or not. Once they've written all the tests, they actually go and write the code. And as they're writing their code, they can check and reference and make sure that it's working correctly because all the tests have already been put into place. So the nice thing about this is that you can write different classes and you can test them separately. And then you can build off of those tests and make sure that they work before you go on and write bigger things. For this class, we're not going to do that. We're writing relatively small things, but it turns out to be very powerful. Everybody with me on this? Sort of? All right. So conceptually, what we're going to do is we're going to be designing classes that solve a particular problem for us. All right? And in this case, I just used the example, since we had that project, of a subject. Any questions so far? How many of y'all think this is going to be a good thing? How many of y'all would rather be set on fire? Yeah, it's better than being set on fire, okay, just in general. So let me show you a little bit about how to do classes. The way that you define a class in C++ is you use the word class. Oh, by the way, let me just tell you, we've also been using classes throughout the semester without really even knowing about it. String is actually a class. IOStream, IFstream, those are also classes. Anything else we've used that's a class that you can think of? Those are the ones we tend to use mostly. The functions that we use in a class are called methods. How do we know when something is a method? When it's a dot, okay? So a function is a piece of code that stands on our own. A method is a function that belongs to a class, and you access by using a dot. So let me just give you a little sense of what the structure looks like of a class. So when you have a class in C++, you use this word, class. That is a C++ reserved word to let you know that you are creating a class. And then you have something here that's going to be your class name. Now when I use this notation, like with the angle brackets, that means you substitute everything that's in there, including the angle brackets. And unfortunately, sometimes in C++ you actually use angle brackets, but that's it. All right, so here's what a uh-oh. You do not use the angle brackets. This is like the generic outline, and then we're actually going to build, we probably won't build a real class this class, but the videos that you're going to be looking at over the next day or two before the next class are all about classes. And then on Thursday, what we'll do is we will write a class, and I will have like some handouts, and you will actually step through code for a class to see how it works. Okay? So, but I'm just going to give you an overview, and this will be slightly repetitive with the videos, but you'll see. Okay, so you have a class and a class name, and the weird thing about classes that's kind of annoying is they have to have a semicolon after the final curly bracket. And that's kind of annoying. Because other curly brackets you don't have to have the semicolon after, but these you do. A class has different things. Inside the class, it has a portion that are called public and a portion that is called private. The public portion is the interface through which anybody who's trying to interact with this component can get it to do things. The private portion is the portion of the class that it's using for its own work internally. Let me think if I can come up with a good example of this. That's not obscene on the fly. So let's say you visit a website, like the Washington Post website, right? What gets displayed on the screen can be thought of as the public stuff, like all the public articles and things like that. But there's probably a lot of stuff in the Washington Post and the website that it doesn't share with you, like the reporter's notes and earlier drafts and versions and things like that, right? So you can think of the public stuff as what's being shared outside the object and ways to interact with the object. And the private portion is the stuff that the object is using internally to do its own computation that you don't want to expose to the world. Now you're asking yourself, why do we have this separation? Is that what you're asking yourself? Does anybody want to ask me that? Why do we have this separation? Well, remember when we're talking about using object-oriented, the idea behind this is that we have big software projects. And what we want to do is, when we come up with our relationship of all these different objects and how they interact, we want to define very narrow and specific interfaces between them. The idea being that if we have well-defined interfaces between them, we can test just those interfaces, and then we know things are working correctly. What we don't want to do is have some way that we're testing things and then have like a back door into there, or some way that other people are getting in and mucking around with the internals of things. Okay. So the reason we have a separate public and private is that the public defines the interface, and the private provides extra space for the object to have things that other people will never be allowed to muck with and mess up. Does that sort of conceptually make sense? Think of it this way. Think of it like we had a bank. When you go to the bank, you can walk up to the teller window, right? And there's certain transactions that you can conduct with the teller window. And those are all auditable by the bank to make sure things happened correctly. What you're not allowed to do in the bank is walk up to the teller window, crawl through, go in the back room, take stuff out of the safe, erase everything in the ledgers, go through people's safety deposit boxes, right? Does that make sense? And so you can think of this in kind of the same way. Like if we were building a class around a bank, the public portions would be the things, the transactions that you can do. You could deposit, you could withdraw, you could put something in your safety deposit box, you could take it out, you could apply for a loan, you could get cash out of your loan. But the private portion would be all the account information, the actual cash that's in there, things like that. It's because you don't want people just going in and mucking with that stuff. Okay. Is that a better example? Now, if I ever had taken a psychology class, and I saw a bunch of people sitting like this, I would take that as like a sign that you all were opposed or defiant. And actually, I did take that class. It never really did me any good. But so, everybody see where we're going with this? This turns out to be powerful. It's a little bit more work, and it's a little bit different way of thinking about the code. That's right. Okay. So then, in public, we can have two things. We can have a data member. And a data member is something like a variable or a number that can just be accessed, right? Because when we're talking about things, they have data and they have functions, which we're going to call methods. So we have private data, public data. Sometimes you can access data members directly. We tend not to use those that much. Or we can have prototypes for methods. And just like we had function prototypes before when we put them up at the top of our code, now the function types are going to be part of the class declaration. And we'll see how we actually build these functions later. But for now, we're going to have public data members and public prototypes for methods. And we'll also possibly have private ones of these as well. So most often, we tend not to use public data members. It happens sometimes, but not always. Most of the time, what we'll do is we'll have methods that will access private data members. And then less frequently, but sometimes we'll have private functions. And these are functions that the class or the object can call to do computation on some of the stuff it's stored internally. Everybody kind of with me so far? There is also something that I will tell you about that we tend not to use here. There's also something called protected. And protected can also have data types and methods, but they won't show up in this class. They might show up for you later. And it's kind of like this in between public and private. Like public, everybody can get at something. Private, nobody can get at something. And for protected, some people can get at it and some cannot. All right, here's what we're going to do. I'm going to answer questions about this for a second, and then you're going to go home and watch videos. And then next class, when you come in, having watched the videos and having a much deeper understanding and overview, we will design a small class, and I will have a handout, at least one handout, that we can do some computation on one and make sure we see how it works. Okay? Everybody good with that? Any last questions? This is going to be very powerful, but it requires a little bit of a different approach to working on things. Yes, sir. So yeah, C++. So the weird thing about C and C++ is that they don't exist as like completely discrete things. Like you can use some features out of C++, but not all of them. And so most programs that are written C++, I actually refer to mostly as C+. That is, they're not pure C++, but they're not C anymore, and they kind of just take whatever features they want out of each. And it's a giant pain in the ass to read that stuff. No, C was not object-oriented. C++ is kind of like the official object-oriented version of C. There are other object-oriented versions of C out there. Anybody ever heard of a device called, what's that thing? An iPhone? Anybody heard of these things? They're kind of trendy these days. The language that you use to write programs is called Objective-C, and it's a different object-oriented version of C. So it's similar. So there are other things out there as well. All right, we're moving into a brave new exciting world. I look forward to seeing you on Thursday, and we'll talk through how to do some stuff.